Hello, we're going to discuss electric flux and Gaussian surfaces. This is Professor Martinez, and thanks for joining. We'll start with electric flux. So electric flux is the sum of E field lines that are incident, that means entering, or leaving surface patches. So we have here an example of a green surface, could be closed or could be open, it doesn't really matter. But what we're looking at is an E field that is piercing that surface, and in some places it may be entering or leaving. In the areas where it is entering, we would consider that a negative flux, and where it's exiting, we consider that a positive flux. But what you need to look at is a tiny patch and understand what's happening. So this pink patch here, which we call dA, represents what we call a differential, or a very small piece of this surface. And it's small enough that we can say that the E field on that tiny patch is going to be represented by one value. So we want to make it small enough that the E field looks constant on that specific spot. We also have one direction that we will choose as the normal, the perpendicular from that patch. So you want to make it small enough that it looks like a flat plane. The angle between the patch is normal, which is the perpendicular line, right, coming out of it, and the E field, which we have as the purple arrow this way, that angle is theta. And we're going to use that in our formula for flux. We basically multiply by the projection of the E field onto that dA vertical, the vertical vector, right? And the total flux is the E value projected onto that dA normal times the value of the area of the patch. It's such a small area that we're going to call it dA. Whenever you see the D in technical documents, it means a differential, a small piece of some large object. Now we have in this cube also, it's another example. This green doesn't have much symmetry, this green surface, but the cube has a lot of symmetry. And we also can see a small patch there. We can imagine it to be microscopic. And we see the normal there is coming straight out of any face that you touch. And in this case, the E field, which is the green arrows here, is parallel to the patch's normal, right? The surface patch. So the multiplication for this is simple. It's the value of the E field times the cosine of 0 degrees. There is no angle formed. It's 0 degrees. So it's just E times the patch's area, right? And that's going to be the flux for that small piece. The total flux for this surface is adding up all those patches. And you will see that the angle and the value of the E field could vary across every single patch. The best thing you can do is just add them up one at a time and update your information for each patch. When you do a large summation like that, and you take the patches to be small, microscopically small, you're doing an integral. That's the concept of an integral in calculus. Now, if things are simple, like with the cube here and an E field that is perpendicular to the normal, we don't need calculus to calculate this. It's simple multiplication because things are not changing across the entire surface. So let's zoom in. Zoom in, get it? And look at this one patch again. This could be on the square or on the cube or on the green surface. And we're looking at the angle theta. And we're just going to drive home the point that the cosine of that angle represents a projection onto the normal of the patch, right? And that means that the electric flux only cares about the portion of the E field that is perpendicular to the patch. I also want to point out this red comment here that we're using this simple formula on the small patch because that's where it's valid. Remember that in this small enough, if it's small enough, the patch will have a constant E field and a constant angle. And that's why we have our simple formula of EA times the cosine of theta. So looking at the angle again in the projection, remember from vector math, vector pre-calculus, we had a dot product. The dot product was two vectors multiplied together times the cosine of the angle between them. And that dot product represented the projection of one vector onto another. It's literally the shadow of E onto A. And you could also think of it as the shadow of A onto E, but that's because it's symmetric. We don't need to flip it back and forth. We'll just stick to this concept, the picture of E's shadow onto A, and that's highlighted in yellow here. That's the E cosine theta. So you notice that if you have the angle of 0, you're getting the maximum value of your multiplication there. The product is maximized. That's why in this case here in the middle, where you have E parallel to the normal, you have lots of flux, but in the diagonal, you have less flux because that cosine theta is going to give you a fraction. And in the condition where the E is parallel to the surface, you now have 0 flux because there is no perpendicular component to the flux at all. Okay? So let's do a simple example of how we calculate flux. Here we have a disk, and we can consider it a perfect circle. And we have an E field that is coming in at some angle. Okay, we're going to use the blue line for the normal to this surface area here, and we're going to find this angle theta. It will be given to us in problems, or we could figure it out using geometry. And then we're going to multiply the E field, which is uniform. You can see from the equal distribution here that the E field is uniform across it. Okay, multiply that times the cosine of this angle, and then you multiply by the area of the disk. It's a circle, so it's pi r squared. It's as simple as that. But remember, the only reason we could use that simple formula for the entire area is because your E field hasn't changed over the entire field, the entire area patch, and your angle is constant. So flux connects geometry to charge distribution. As you can see, we're now combining two things, and it gives us a little bit more information about how a field is behaving, right? But it doesn't tell me anything about the strength of the field, because that's not what it's designed to do. Okay? It's a global measure. As we said, it adds the contributions from the entire surface, right? Remember that inward portions are negative, and things, the flux pointing outward would be positive. They can cancel out, which tells you that you can have a very strong E field and the net flux is 0. Okay? So flux does not tell you directly about the E field, right? It's another type of measure, but we will see how it can be very useful to us when there is symmetry. So use this analogy of a river rushing around an island, okay, or through an island. The flow can be strong, but if I'm asking you about the net flow in and out of the island, it would be 0 because what comes in comes out, right? That's what flux is about. It's about what is the net crossing and not telling me about the speed or the strength of what is crossing. So we're going to understand what's so important about flux, right? What's all the fuss about flux? Well, it's because it can tell me the source of the field. It can tell us about the source, even though it can't tell me the size. It's like a charge detector, but it's not a field meter, right? So if there's a charge inside of a surface, regardless of how complicated the field can be, I will know it because the flux will not be 0. I will know for sure that there's a charge inside. And likewise, if there is no flux, then you know there's no net charge anywhere inside the surface. Secondly, the flux will let us find the electric field in some situations, as I mentioned before, where there's supersymmetry. And then we're going to use Gauss's law in combination with the principle of flux, right, to tell us what the E field is, right? So that's where we're going to focus on next. Let's look at the flux from a point charge. So we understand this Q, this charge inside of this blue sphere rather, is going to have a radial electric field pattern. Okay? Now, the field radiates outward uniformly from that point charge, and it has a constant magnitude everywhere over the sphere. The flux through the sphere is definitely just the E value, okay, times the surface area of the sphere, 4 pi r squared. Now remember, be clear, I didn't say that the E field is constant everywhere in this volume. We're not talking about the space inside the blue sphere. We're talking about on the sphere itself. This surface area has a constant E field. It is an equipotential surface, if you would, right? And so now I can calculate the flux by simply multiplying the total area times the total E field. I mean, at any given point, the E field times the total area. Okay? Now understand that this is a special case, right? Where I can use this because of the symmetry. Because of the symmetry. Okay? And that's very important. So what, you might ask? All right, well, let's ask the question of so what? Gauss's law now comes into play because the total electric flux through any closed surface always equals, this is a constant no matter what kind of surface or E field you've got, it equals the Q enclosed by that surface divided by the permittivity of free space. So here's what it looks like. I am going to use Gauss's law now, okay, in combination with what we just solved for using simple flux definition, and I'm going to combine them to solve for the E field. So let's read the bullets. If we know the flux through a surface, and it is simply related to the E field, right? It's a multiplication problem. And we know the Q enclosed. And then we can solve for E just by dividing, right? It's simple algebra. All of these things were true because of the symmetry of this problem. Now, if the electric field is not uniform, we usually cannot solve for it by itself, but we can still use Gauss's law to find out things about the flux in symmetric parts. So let's get a cube a try. Let's look at this charged cube. First, notice that charged cube is not going to have a uniform electric field because of the edges and the corners. We've learned that fields concentrate on conductors at sharp edges or corners. You can see by this colorful diagram here how it's going to be very strong. The red represents intense, very strong concentration of field lines at every corner. And the edges will also experience the same concentration of field lines. Not only that, but your field direction is going to be changing as you get closer to corners and edges. You go from being perpendicular to the surface to coming out at an angle. So Gauss's law tells us that the total flux is going to be related to the enclosed charge divided by epsilon naught. Now here's where we will use symmetry. The 6 identical faces of the cube will ensure that the flux distributes itself equally. That didn't say the E field did, but the flux does. The flux is independent of surface shape, okay? And it's simple, even though the electric field is not. All right, so we know the flux only depends on the enclosed charge, not on the shape, and we're going to use Gauss's law and symmetry to decide that the flux through any surface, the face of this cube is going to be 1/6 of the total flux. There are 6 faces of a cube, so it should split evenly. The flux through any face is 1/6 of the total flux. So that means it's Q over epsilon naught divided by 6. Please see how you can use that information to solve this problem. So, in order to solve this, we need to think of this problem symmetrically. So the first thing we need to understand is that the point charge is not going to have any field lines piercing the faces that are aligned with its axes. So this is a nice diagram. It's a slightly different configuration. The point charge here is on the left top corner, but it serves the same purpose. You can see that the arrows of the field lines that are going to pierce the faces are all going to come through the front, the bottom, and the back side, the back side here. So if H, G, C, D, that plane is going to see piercing, the bottom plane obviously, and then the face FGCB. Okay, so we're only thinking about 3 sides, honestly, when we're looking at the flux here. So you can think of it as the outer faces. Okay, the outer faces. The other thing you need to look at is that this piece of the puzzle is 1/8 of a total cube that would have had the center charge. Right? So if we're only thinking about the outer faces, right, and this represents 1/8, right, of the total cube. So we can do some math very simply now. We know that we have in one face of this large cube, we have Q over epsilon naught divided by 6. That is the flux coming out of one face. Now this is 1/4 of that. So I'm going to draw this out so we're clear what I'm talking about. This small cube here is 1/4 of that flux. So that would give us Q over epsilon naught 6, that's the whole face, and then you multiply that by 4 to get 1/4 of that. Now, if I am actually dividing this in half, because the triangle is half of the square here, then that's actually half of that. So we're now looking at 48. 6 times 4 is 24. When you multiply that by a half, you get 48. Q over epsilon naught times 48. That's just one face. Okay? We also were asked to consider the top. It's exactly the same math. So you double it, and now you have Q over epsilon naught divided by 24, right? When you multiply this by 2, the 2 simplifies with the 48 to give you 24. So that's how you'd solve this problem using symmetry. And the question was about the flux, not the electric field, because there's really no way for us to get the electric field because it is not uniform. So let's just review. This is where we started. I have my charge here in the back corner, and I need to know how much flux is coming through these 2 triangles on the top and the right face. Answer choice 2. Now, the conditions for simplifying flux expressions. Now we're going to simplify to have that beautiful E times A times the cosine of theta. We saw that we could get that if we had a tiny patch, right? But we'd still have to add up many tiny patches to get a total flux value. And each tiny flux patch could have a different E value or a different theta, which means that E would be complicated to pull out from that total value of flux. But when everything is constant, then you can factor out E and get information about the electric field, right? We're going to solve applications now using Gauss's law, where we can actually solve for the E field. We're starting with this, which is an extremely important application. It's important that you master this example. So we're going to look at a sphere. It's actually a solid sphere, but there's a cavity in the center that's empty. And we're going to put a charge on the outer shell, okay, at radius R2. The charge is 7 microcoulombs. Now, I am going to find the field inside the cavity, the field inside the conductor, which is the gray section, and the field outside the shell, okay, where we have a positive charge. First, ask yourself, can Gauss's law help me with this? I.e., can I draw a surface around the charge that has a uniform E field, that means magnitude and direction, everywhere through that surface? Okay, let's see. Well, I think that the answer is pretty obvious. We're going to take another sphere. Okay, we're going to take another sphere. We're going to draw it. Let's look at the outside shell first, even though it's part C, but that's going to be pretty straightforward. We'll take the outside shell here, and we are going to, this is supposed to be a circle, okay, a sphere actually. And we're going to imagine the radius, okay, outside the shell, so I could take the radius of 20 meters. It's arbitrary. They didn't tell me a value, but let's say they asked me at 20 meters. I know, according to Gauss's law, that the Q enclosed over epsilon naught is equal to the total flux, okay? And that flux is also equal to the E field, okay, times what is the surface area of the sphere that I just drew? Well, it is 4 pi times the radius that I'm checking for. It's extremely important at this point that you always use the radius of the location that you're checking for. Remember, you're trying to find an E field at a certain spot. So the R in this sphere that I just drew has to be the distance that you're interested in. So we said 20. We're going to look at 20 meters. So we take 20 squared. The surface area of a sphere is 4 pi r squared. 4 pi r squared. So that, excuse me, sorry, that is very messy. Let me clean that up. Okay, I can dictate that. So it's 4 pi r squared times the E field, which is the mystery we're trying to solve. And I have the Q inside. It's 7 microcoulombs. And we divide by epsilon naught. You take that value and voila, out comes your E field. How are we going to do this? We're going to divide by the 4 pi r squared. Okay. And that R is 20. Okay. 20 squared. And now we have a magnitude for the E field at 20 meters. Okay, this is a calculator problem at this point. Notice that the cosine of the theta was not in the equation, or was it? It was in the equation. The angle is 0 because the E field is going to be perpendicular everywhere on that sphere. So the cosine of 0 equals 1. All right, this is why we have such a simple formula for this situation. Now, what about inside the conductor? So we're going from C to B now. Let's pick a radius inside. Why don't we pick 12 meters? So inside, we're going to see the same Q over epsilon naught, but wait, the positive charge is on the surface, outermost surface. There is no Q once you go underneath the surface. Therefore, the total flux is 0 everywhere inside that conductor. Now, the last question is about the field inside the cavity, and basically we're repeating ourselves. If we draw a circle, a sphere rather, right? This is a sphere inside here. There is no charge. There is therefore no electric field. All right, now let's move on to a more interesting example. Now we're going to have the charge move to the center. Okay, and we're going to ask the same question. Can we use a Gaussian surface? Excuse me, going ahead. Can we use a Gaussian surface, right, to solve this? It's the same symmetry, guys, so we definitely should be using the same surface we had before, right? So we're going to use the sphere around the inner cavity, right? Sorry, the inner cavity, and we're going to take any, if I ask you for the electric field at 5 meters, then you would use that radius for the sphere. And you would use exactly the same math we did before. Take the surface area of that 5 meter radius sphere. Multiply that by the E field, and that's your flux. That's the E field that I'm trying to solve for, right? And then I'm going to set that equal to Q over epsilon naught, which is what Gauss's law tells me. Okay, so the flux is equal to Q over epsilon naught. That's Gauss's law. And the flux definition is surface area times the E field equals flux. So we're putting those two things together. Okay? So we have surface area times E field equals flux. And we also know that that's the charge enclosed divided by the epsilon naught. Okay? That's Gauss's law and flux working together. Now, why can we use this simple formula? Let's keep reviewing that. It's because we have a perpendicular E field to the surface everywhere and a uniform magnitude of that E field. Right? So that's going to give us a simple solution there. We can get the electric field inside the cavity. It shall be equal again to Q over 4 pi r squared epsilon naught. And now inside the conductor, we would do the same thing now, but there's a small difference here. Look at what happens. We're going to have an induced charge on the inner surface of this conductor because of the Q that's in the center. Now, guess what? If you take a circle anywhere inside the conductor, you will now have enclosed the negative 5 microcoulombs of charge plus the positive. Guess what? You have zero net charge, which also means zero electric field inside that surface. So even with the point charge inside the cavity, the conductor has zero electric field inside of it. Now, if I have induced a negative charge here, where did the positive charge go? If it's negative, it's because there's some positive charge that ran away, and it ran to, where'd it go? It ran to the surface. So we now have the 5 microcoulombs on the surface. And we're looking at the same problem that we had in the previous slide, where we're now looking, if we go to the outermost shell and go outside of that, maybe 20 meters again, we're looking at a net charge of 5 microcoulombs. Why is it net? Because this is a negative 5 microcoulombs right in here. Let's change the color to blue. This is a net negative 5 microcoulombs on the inner surface that's induced. And then we have the red Q in the center, which is positive 5 microcoulombs. Okay. So what we're looking at, if we go outside, we're going to see anywhere outside the 15 meter mark, we're going to see 5 microcoulombs. Perfect. All right, so we're going to clear these drawings and move to the next example. Now I'm going to put the charge in the center, and I'm going to put a net charge on the outermost shell. Well, let's talk this through quickly. We're going to have the induced charge on the inside of the conductor just because of that center charge, the cavity's charge. Same thing happens. So it's going to be a negative 5 microcoulombs sitting here on the inner surface. That's induced by this. Okay? Induced by that. That means that we have 5 microcoulombs that have moved to the outer edge of this donut here. So we have the 10 microcoulombs that we added to it. We deliberately put it, and then we have another 5 microcoulombs that's induced. The total charge is 15 microcoulombs, just as you would have suspected. It's that simple. So all the math remains the same here. We won't belabor the point. You're going to simply total up all the charge enclosed, divide by epsilon naught, set that equal to the surface area of a sphere that we would draw at whatever radius we were asked to go to. So if I want to know the electric field at 25 meters, then I would do 4 pi times 25 squared. Okay, r squared. So that's 25 squared. So the electric field there, I want to make sure you're clear on this. 25 squared. This is my surface area, and I'm going to find the Q enclosed of, it's 15 now. Okay, very straightforward. 15 microcoulombs. And we're dividing by epsilon naught. Okay, and that equals the electric field. So I did skip the step where we equated the electric field times the area to Q over epsilon naught. I just went straight to the solution where I solve for E. Okay. All right, I apologize for the poor handwriting. It's a mouse issue and not really me. Okay, let me try to improve on this. All right, that's B. This 25, remember, is the radius that I'm asked to find the electric field at. And it's an equipotential surface, so the electric field is constant everywhere on that sphere. Everywhere on that sphere. All right, we clear these drawings and we move forward. Okay, we have found all the places. Now we're going to look at a line charge. We've examined this before qualitatively, and we understood that the net field will point up perpendicular due to the symmetry of my line charge. And this is going to be a very long line charge. So I'm going to stay towards the middle and not go towards the ends. You might want to even think of it as an infinite line charge. Okay, so this is like a charged rod. All right, so we now have net E field pointing perpendicular up from this line charge. I would like to know the electric field a distance r away, some height, some distance r away from the rod. And I'm going to be given the charge density of the rod. A charge density means that you take the total charge and you divide by the area. So that'd be Q over the total area that you're given. That's a charge density, right? So I'm going to be given that information, but right now I want to ask the important question. Can I use Gauss's law to help me find this electric field? In other words, can I draw a surface around this charge that has a uniform E field, magnitude and direction, everywhere through the surface that I'm drawing? All right. The answer is yes. The cylinder I've drawn here in green is going to give me the perfect symmetry for this rod. The E field is pointing perpendicularly up from the rod. And along the faces, the circular faces of the cylinder, the E field is going to be, it's going to be parallel to that face of the circle. So the flux there will be 0. I can ignore those faces. There will be no flux through those circular faces. So the only portion of this surface that counts is the body, the curved body of the cylinder. That's where the E field is perpendicular everywhere. And it's uniform in magnitude. Okay, so now how do we figure this out? Well, okay, we're going to, let's go back. Okay, we're going to take a certain distance r, that's going to be given to us by the problem. Okay, and we're going to find the surface area of the cylinder, right? We're going to be building our flux equation. So the surface area of the cylinder, and we're also going to be using Gauss's law to get so that means we need the Q enclosed. And if I'm going to draw the cylinder a certain length L, if I know the charge density, and I'm going to call that lambda, that's this figure here, lambda. Okay, this right here is lambda. Okay, so if I know lambda, which is going to be a charge per unit length, then I multiply by L to get the total charge inside my cylinder. Now, that surface area is the only thing left to get, and I see a typo, forgive it. The surface area here is going to be 2 pi r, which is the circumference of this circle here. And I'm going to imagine that circumference being pulled back across this distance L, right? Just imagine that you're taking the circumference. It's not the full circle now. It's just the perimeter. And you bring it back the distance L. That's the surface area of a cylinder. Okay. And I am going to erase this. That's a typo. Okay. So the surface area is 2 pi RL. Now we put our flux equation together and we use Gauss's law. The flux is the electric field times the surface area. The Gauss's law gives me the charge enclosed divided by epsilon naught. Put them together and voila. We can now cancel out the L's and divide by 2 pi r to get the electric field. Notice this is different than the point charges formula. It's different. Okay. Notice this is different. There is no r squared in this formula. Right? So we need to see that electric fields can differ depending on the geometry. Okay. So now I'm going to do one more example. I hope that you're going to get a big surprise from this one. The electric field in a uniform infinite sheet of charge. So I'm going to find the electric field a distance r away from this sheet, and I will be given the charge density. Notice the line charge symmetry is going to help us here. We know the E field is perpendicular to the sheet because it's just a bunch of line charges. You just have to think of them as an infinite set of line charges. So now let's go. You know the drill. What do we ask first? Can Gauss's law help me with this? Is there a surface that I can draw around the charge that will have a uniform E field through it? Yes. Now we're going to use the cylinder again, but this time we're going to reorient it. We're going to turn it so that the flat sides are going to be above the sheet and below the sheet. And I'm telling you the charge density. It's going to be called sigma now because it's going to be per unit area, right? So per square unit. And I am going to pull this cylinder up a certain height, which we can call R or L. It doesn't really matter right now, but I'm just going to bring the cylinder to a certain distance away from the sheet. And I'm going to use that to figure out my E field. All right, here we go. So first thing, what's the Q enclosed by the cylinder? We use the sigma and you multiply by the area to get the total Q enclosed. Then I find out my surface area so I can use my flux equation. The surface area, can I just tell you, it's going to be A, which is the area of the circles. I don't want to figure it out just yet, and I'm going to show you why in a minute. But let's just carry around that symbol A. Why don't I care about the surface area of the curve now? The curved body. Well, remember, flux only cares about E fields that are perpendicular to the surface. The E field is crossing the circular flat sides of the cylinder. There are no E fields crossing the curved body. Okay, that makes life very easy. Remember, there is no E field that points any other direction but straight through the circular flat top and bottom. So those are the areas we take. So the surface area, I'm going to call it A, and there are two of them. So that's going to be 2 times A times E. That's the flux. The angle, again, is 0 because they are perpendicular. Now I equate that using Gauss's law to the total Q enclosed. That's sigma times A. Divide that by epsilon naught, because that's Gauss's law. It says the total enclosed Q divided by epsilon naught equals the flux. And now do a little bit of algebra, and hopefully you're as surprised as I was the first time I saw this. The A's cancel out, and there is no dependence on distance. The E field is equal to this surface charge density for the flat sheet divided by 2 epsilon naught. That's pretty amazing. But now you should be able to understand why the E field through 2 parallel plate capacitors is constant regardless of the distance. The E field is constant. That's pretty cool.